So, hi everyone. If you hear me, then please tell me. Cause, please tell me if you hear me. And we'll be starting in a few minutes. We'll be talking about solutions to problems A to D. Cause I didn't manage to solve anything other than AD. Well, E isn't my kind of problem, and F was kinda hard for me, so yeah. Also, I think this contest was unbalanced, as you can see. Well, E have 10 times less solves than D, so it's a big gap. Okay. So first to problem A. In problem A we are given n sticks, each stick have its length, and we want to say how many regular equal-sided polygons we can construct from those sticks. Okay, so basically we can notice that it's always optimal for us to create triangles, because basically we can create a regular polygon from 3 or more sticks of the same length, right? So, well, we see that it's always optimal to take 3 sticks, because we take as little sticks as possible. So, well, we can count for each length of stick, we can count how many times this length appears, and our answer will be sum over all possible values and count of how many sticks of length I divided by 3, and we want to take a floor of that. Right, so this means how many triangles with side of length I can create. So, yeah, I hope everyone understands. It was easy problem. Basically, the only observation is that we only want to create triangles. Okay. So, now to problem B. I don't think there are any questions. Well, in problem B, we want to construct a sequence A of length n, such that its sum of the numbers in this sequence is equal to k, and the number of bits that are on in binary representations of OR of this array. So basically, we have 1 on some position of OR if there is at least one, yeah, okay. So, problem B. So in this problem we want to construct sequence of length n with sum equal to k, and we want the number of ones in the binary representation of OR of this array, of bitwise OR of this array. We want this number of ones to be as large as possible. So basically the property of OR is that in our OR we have x or kth bit set to 1 if and only if, well, at least one number have k set to 1, right? The kth bit set to 1. So, yeah. So using this property we can notice that well, we will always want to stuff all the bits into one number, right? And we want this one number that will have all of our bits to be as small as possible. So, well, we can notice that we want the number that looks something like this on binary representation. It's only like it doesn't have any zeros, right? So yeah, so we know that this number, if it has length n, it's 2 to the power of n plus 1 minus 1, right? And well, we want to find the last n such that 2 to the power of n plus 1 minus 1 is at most k. And our array will look like this. We have our array will be 2 to the power of n plus 1 minus 1 and only zeros. But as you can see, well, the sum of this array may not be equal to k. So it won't change the OR, but we also need to add as the second number here k minus 2 to the power of n plus 1 minus 1. And now we know that our sum is equal to k. So does anyone have, well, do you see that this construction works? Okay. Okay. I think everyone understands. Well, those are easy problems. I think that problem C was unusually hard, at least for me. Usually it took me problem C usually takes like 10 minutes for me, and now it took me 35 minutes, so it was hard. Someone wants problem B to be shown again. Well, I can repeat quickly because it's easy problem. Basically, the observation is that when you have our OR of array, so A1 or A2 or AN, basically we have case, like when we have this OR in bit representation, the kth bit of this OR is set to 1 if and only if some of the A's have this bit set to 1, right? And well, the observation is that we'll always want to, exactly one number will have this bit set to 1, right? Because it gives us the smallest sum. And well, so we can say that one number have all of the bits set in OR, right? And well, this number will always look like this. It won't have like holes. It won't look like this because it's not optimal. It's bigger than this number. And what we'll do, because we see that k can be different from 2 to the n plus 1 minus 1, well, we'll also add this number here. It won't change the OR, but it will make the sum equal to k. So that's it. Yes. So to problem C. In problem C, we have grid of size n by n. So let's say n is equal to 7 or something. And in one move, we can choose some square such that there is nothing in like there is nothing that attacks this square, and we know that we can choose some square if there's nothing in its row and there's nothing in its column. And we can color that square to, let's say, blue. And also the mirror reflection of this square will be colored red. So we could choose like this, and then we could choose, let's say, like this. Then we know that the mirror reflection will be here, right? We know that if we color the square in row R and in column C, then it will, if we color this blue, then the square in row C and column R will be colored red, right? Okay, but also if we color something on the diagonal, then, well, it doesn't have reflection, so it will only be colored blue. So basically, we are said that already some of the moves were making, right? So, well, we can start with something like this. Oh, I made a mistake here. And we want to say, if we'll make some moves until we can't make any moves, until we can't make any valid moves, until there are no valid moves left, how many ending boards we can get from, let's say, this. So I hope everyone understands from something like this. So basically, observation is that, let's say that at the beginning we have some available rows and columns. So let's say that in the beginning we have all rows available. We can put anything on those rows up to n. And we have any column available. So what our operation does, if we are picking something that have the same row and column, then basically we are just deleting this row and this column, right? But if we are picking something with different row and column, so let's say 1, 2, then we are deleting, or let's say here, it will be 3, 5. Then we are deleting the third row, the fifth column, but also the third column and the fifth row, right? So basically what the operation does, it deletes 1 or 2 positions from this row column, right? It can delete both 2, both 3s, or maybe only 5s if it's on diagonal. So basically what we are left with, some available rows, let's say 1, 3, 5, 6, but also the columns that are available for us are the same, right? So it will also be 1, 3, 5, and 6. And now we want to, knowing that what the move does is, we know that now the moves are delete some values, right? So we can delete one value from both, or maybe we can delete like 2 values with the same move, right? So basically now we are given an array, and in one move we can either delete 1 value or we can delete 2 values, but like with different colors. And now, well, we want to say how many different, we can delete 1 value with red color, or we can delete 2 values, and one of them can be with red color and one of them can be with blue color. And we want to say how many different colorings do we have. I hope everyone understands this. Okay. Yeah, I hope everyone understands this. So basically it's combinatorics problem. So what I have done, I have we can iterate in our sum on how many elements we like delete separately, not in like pairs like here, but how many elements we delete, how many rooks we place on diagonal, right? So we know that if we put I rooks on the diagonal, then then we have to choose from, well, let's say that our array length is n, right? So here n would be equal to 4. It's like another problem. So let's say that we are, or wait, maybe I have overcomplicated it. Yeah, I have overcomplicated it, I think. Maybe? Yes, I think so. Because basically we can notice that we can get every division in which, well, there is less blue colors than red, right? We can get it. So basically our answer will be, we'll be iterating over the number of blue colors. It can be at most n divided by 2. And well, we want to, from n values, we want to choose I blue values. No. Sorry. It doesn't work like this, because we also want to know in which pairs it is. So basically, we have our array 1, 3, 5, 6, and we want to divide it into some. We want to divide it into some numbers that will be alone and some pairs. Like we could have this pair, and this number could be alone then, right? So we could iterate over number of numbers that are alone. So in this case, it would be 2. And well, first we need to choose the number of numbers that are alone. So we would like to do n choose I, and we want to multiply it by dp from I. And what is dp from I? Well, dp from n minus I, sorry. dp from n minus I would mean how many ways are there to choose n minus I pairs from n minus I divided by 2 pairs from I numbers. From, well, dp from I, to choose I divided by 2 pairs from I numbers, right? So how to calculate something like this? Well, when we have our sequence, let's say it's 1, 3, 5, 6, then we can notice that we can choose first pair in like n times. Well, we can choose first pair in like n times n minus 2 ways, right? So we just choose 2 numbers. You see, the order is important because one of them will be red and one of them will be blue. So, well, basically dp from I is, wait, yeah, but dp from I is equal to n times n minus 1 times dp from I minus 2. So it's like factorial, right? But also you need to notice that, well, when we have some set of pairs, let's say we divide them like this, in this formula we'll calculate we'll calculate like both orderings. So we'll calculate these ones and these ones, and well, those two are the same for us. So we also need to at the end we need to do dp from I after calculating. So well, we know that dp from I is just I factorial divided by I divided by 2 factorial, right? Because, well, this is what comes from formula. Yeah. Basically, we first choose pairs and then we divide them by the number of orderings. So that's the whole task. I hope that... Yeah, it's not a good problem C because it required too much combinatorics, I think. Basically, we notice that what we do in one move is we either take some row and column that are the same and we color them blue, or we take two rows and columns and we color one of them blue and one of them red. And basically we do combinatorics to count the number of ways to do this. So yeah, that's just it, basically. Yeah. So, and well, yeah. Well, maybe I will say how to calculate the number of ways to choose I divided by 2 pairs. Yeah, someone wants an example, so I will show. Let's say that we have 4 by 4 grid, but none of the cells are colored. It's possible. And we want to show the number of ways to do this. So, basically, at the beginning we have those 4 rows available and those 4 columns available. And well, in one move what we can do, we can either choose like 2 blocks and color one of those blocks red and one of those blue, or we can choose one block and color it blue. So, well, we can first iterate over the number of things that we put on the diagonal. So we can iterate over those blocks that have like the same row and column, right? And well, we can pick which one of those are on the diagonal. So it will be n choose I, right? I is the number of things that we put on the diagonal. And then we want to calculate dp from n minus I. So for the other, let's say, 2 guys, we want to, let's say that on diagonal we put like those guys on diagonal and those guys on diagonal. And now we want to calculate the number of pairs that we can divide those 2 into, right? So I say that, well, we can choose the first pair on n times n minus 1 divided by n times n minus 1 ways, right? Because, well, I can either choose, so here it will be 2, because I can either choose 3, 4 or 4, 3. How do they differ? Well, on this picture, picking Picking for 3 would mean that we well, basically give our rook in the square for free. So it will be something like this. And the other way would be to do something like this. They're like symmetrical or something. So basically we see that dp from I is equal to dp from I minus 2 multiplied by I times I minus 1. But, well, we have also calculated each like ordering twice. So if we would have like the array of length 4, then, well, one possible division would be like 1, 2, 3, 4, but we would also calculate 3, 4, 1, 2. So we need to divide it by the factorial of the number of pairs, and the number of pairs I divided by 2. So yeah, so basically dp from I is equal to I factorial divided by I divided by 2 factorial. So yeah, that's it. So I hope everyone understands. If someone doesn't understand, then please look to the editorial or ask the question maybe on chat, or just rewatch the stream, because it will be saved. So now, but I think that problem C was not good for its tier. It required combinatorics. But outside of this, it was normal C. The combinatorics took me probably like 25 minutes of the 35 minutes I spent on problem. So now to problem D. So in problem D, we are given an array. So let's say, 7, 3, 7, 2, 1. And we want to calculate the number of tuples L, X, R such that XOR on interval LR is smaller than XOR on interval Lx, XOR or on interval XR, right? And well, XOR on interval LR is just right? So it's just something like this. So we can notice that the thing that we have here is just, well, we can see that the only thing that appears twice is A from X. So basically it's just XOR of all numbers from L to R, but without AX. So now we want to think of when the XOR of all numbers from L to R is smaller than XOR of all numbers from L to R, but without number AX. So without number X. Well, I can prove to you that it only appears when MSB, so the most significant bit of AX, so if MSB from AX, so this only happens if MSB from AX doesn't appear in XOR from LR. How to prove it? Well, let's look at, now let's say that this is XOR from LR. And this is A, X. Write it in binary, of course. So what we can notice is that here we have MSB, and if it turns something on, then we know that even if I zero everything after MSB, it will still be bigger, right? Because MSB is greater than everything up, than sum of everything up here. So, well, now we've proven that it happens if MSB doesn't appear. But what happens in the other case? Let's say that if we would have 1 here and only zeros here, and only ones here. So we see that what would happen, well, this bit would be zeroed and all of those bits would be set to 1, but it would still be smaller because this bit is greater than all bits here. So basically we have proven that this happens if and only if, well, this MSB doesn't appear in XOR from L to R. Right? So now we want to calculate for each x the number of intervals that contain x, such that, well, the number of intervals with, so we want to basically calculate the number of intervals that contain x such that, well, MSB doesn't appear in their binary representation. Okay. So, yes, when MSB, so we will iterate over our MSB from 0 to 60, and we'll calculate prefix sums of, well, how many times this MSB appears on some interval, right? Because I know that MSB won't appear on XOR from L to R if it will appear even number of times on this interval. So we know that when we have some x and we consider those prefix sums, right? We want to consider prefix from some R minus prefix from L minus 1. And, well, we'll calculate these prefix sums only on like 0, 1 elements. If 2 to the power of MSB appears or it doesn't appear. So we know that we want to now calculate for x such that, well, the bit that we are in is like MSB of x. We want to calculate the number of pairs RL such that P from R minus P from L minus 1, well, it's like even. Is even. So, well, it's even when both of these have the same parity, right? So we want to calculate the number of even things to the left, even things to the right, and multiply them, and also calculate the number of odd things to the left and odd things to the right and multiply them, right? So even times even and odd times odd. And, well, we will calculate those prefix sums for each possible bit, right? We'll calculate for each x, like going from left to right. For each bit we'll calculate the number of odd prefix sums up to this point and odd prefix sums up to this point but from the other side, and then just multiply them, and the same for even. So yeah, the main observation in this task was this, that, well, we only want to look at MSB, none other bit interests us. So yeah, that's Anyone have any questions? I hope that everybody understood. I'm sorry that today's stream will be so short, but I think that today's solutions were really short. Yeah. And if someone wants to know more, they can join the Discord server. And stay tuned for more on this channel. Yeah. Does anyone have any questions? If MSB appear even number of time in lesser XOR, then also does it matter, or does it matter? It only matters. I don't understand the question. I'm sorry, but well, we have shown that it only matters on the most significant bit of AX, right? It's some easy prefix sums. Speed up to don't have like n squared or n to the power of 3, but to have like n times number of bits. So thank you. Do you have like any questions? Maybe to some other task? I can show you code if someone wants. I don't see any questions. I'm sorry for like this stream being so chaotic, but English isn't my native language, as many of you have noticed. So, thank you for today's stream. Stay tuned for more on the channel. Sorry that it was so short, but I didn't know what to tell. Like, I didn't know what more could I tell. And stay tuned for more on this channel. Well, after this contest, I will probably be candidate master again. I will probably be around 1950, but my peak was on master, and then I had some bad contests, really bad contests, especially this one, and this one was bad for me too, because I booked one of the solutions, but I think I will be back in master soon. On this contest, as you can see, my performance was around 2200, and yeah, I hope that it will stay this way and I will be back in master in no time. So does anyone have other questions? Because I would be happy to answer your questions. So thank you for staying here with me. And oh, what's your LinkedIn? Okay. Well, I don't have LinkedIn. I'm 16, so yeah, I don't have LinkedIn. But yeah, I don't have LinkedIn. Someone wrote that C problems come from DP and combinatoric variant for me today. Yeah, I think C required more combinatorics than normal CF round C. Like, well, it required unusually much combinatorics for this tier. Because many times C is, well, just, I don't know, C is just some easy observations with maybe a little bit of implementation, but usually not combinatorics. So also stay tuned for more on the channel, because there are, I think, many educational series that Cheyenne does, and I think those are pretty good. Oh, there's a question. At what age did you start CP? Well, I started CP when I was in 7th grade. So I was 14 back then. Yeah, I was 14. Now I am. Well, I will be 17 in. No, I wasn't 14. Wait. No, I think. I was 14, I think. And now. Wait, something. Because I am doing CP for 3 years, I think. Yeah, I'm doing CP from 3.5 years, so pretty long, I think. And yeah, so I started it when I was 30. 13, sorry, 13. I started it when I was 13. Yeah. But as you can see on my Codeforces graph, well, I wasn't much progressing here. But I was also rage quitting contests, etc. I was pretty long in newbie. And then I progressed fastly to expert, and then I was in expert for a long time. And then I progressed fastly to master, and I hope that I won't be long here. I will be in GM soon, I hope, but it will be very hard, because I'm not on this skill level yet. Yeah. And I'm from Poland, if someone wonders. Yeah. So I hope I will be given opportunity to stream more things to you. Oh. There are many new Codeforces rounds that are scheduled, so that is nice. Well, I think in pupil range what is most important is just solving problems. So just pick problems that are, well, if you are like rated 1000, then you should solve probably 1200 problems or something like this. Choose problems that are slightly above your rating, or maybe problems that you want to solve, and just solve them. But you must do this. You must solve such problems that they won't be too easy for you, right? Because if they will be too easy for you, then you won't progress at all. So just go to problem set and solve problems that are not too hard and not too easy for you. If some problem is too hard, then solve easier problem. If it's too easy, then solve harder problems, and that's it. Yeah, I think you should just solve over Codeforces rating, and I think if you solve 50 problems that are like hard for you or slightly hard for you, then you should be in pupil. I think that just works like it. But you can't solve too easy problems for you. So if you say you solve at least 2 problems in div2 problem, if div2 rounds, then you should solve, I don't know, around 1400 or something like this. And try to solve as many 1400s as you can by yourself. Yeah. Yeah. Thank you for asking your question. Yeah, so I got kicked out, but thank you for asking your questions, and see you next time. Stay tuned for more. And I'm sorry for my English. My English is bad, but thank you. Oh, someone asks for F solution. Well, I haven't solved F. As bonus, well, if someone wants to, I can show how to solve f on how to solve f on array, maybe. So basically, to solve problem f on array, so basically we have problem f1 on array. Basically we have numbers in an array, and you would like to say are those two intervals different? Is there some values on those two intervals such that it appears different amount of times on both of these intervals? So for example, here one appears 2 times, and here it appears 0 times. And if there is some value like this, then output this value. So what we could do merge sort tree on interval. So basically in node that contains interval LR, we will have sorted values on this interval. Here it would just contain values on this interval. And then if we have nodes that if we have nodes that correspond to this interval, let's say that we have some node that has 1, some node that has 1, 2, and well, here we can have something like this. Then we will just want to bin search and find the longest first prefix such that the hashes on this prefix are different or something. Because we can also, well, keep hashes of every node. Well, it's kinda, yeah. I just said it quickly because I haven't solved F1. So if someone wants to think about it for array, there is something like this. So thank you and see you next time.